So thank you very much for joining us today to our webinar together with Pemtoprinט and Rolando Ferrini. Our webinar today will be on micro-optics and new design possibilities. Thanks, Rolando, for sharing your presentation. Dr. Rolando Ferrini, can you go to the next slide, Rolando? So just as a quick intro to anyone who is not yet familiar with the Zoom webinar platform, you have below a Q&A button. You can there ask any questions during the webinar, and we will have a few stops during the webinar where we'll answer your questions, and also in the end of the webinar we'll answer all of the questions. Also, the webinar is being recorded, just for you to know. Go ahead, Rolando. So quick intro regarding Rolando. So Rolando joined Pemtoprinט Neuchâtel earlier this year as the head of Pemtoprinט Neuchâtel. It's a new division of Pemtoprinט, and this division is devoted to the development and commercialization of photonics-related micro devices in glass. Rolando has a PhD from more than 20 years ago. He was a senior research associate at EPFL a long time ago. Later on, he was at CSEM. He was a group leader at Micro Nano Optics and head of focus area photonics. Lately, in the last 3 years, he founded Fabulous pilot line, which is a manufacturing of freeform micro-optical components. So he was the founder of this pilot line. And we're happy to have Rolando here to talk to us. Go ahead, Rolando.
Thank you, Aviatar. Thank you for the introduction. Then we can go to the agenda of the webinar. So just quickly to have kind of a menu, I will start telling you a few things about Pemtoprinט, about the technology of Pemtoprinט capabilities and performances. And then I will go through some examples that clarify what are the performances and the capabilities of our technology. And I divided in 4 chapters, what I call optics components, and also wafer tooling and masters, which is the core for micro-optics. But then I will also tell a few things about other components that are necessary if you want to integrate micro-optics in your devices. And these are going to photonics components, fiber components, and integrating systems. And one thing that you will hear today very often, and I would like to highlight immediately this point, is integration, monolithic integration. If there is one take-home message that I would like to give immediately, is that the Pemtoprinט technology is really super trooper when you want to integrate more functionalities in the same component. And then I think at the end we'll have the Q&A session. Now, it's good to start from some challenges. What are the challenges that you may have that Pemtoprinט can help you to solve? What are the challenges for Pemtoprinט where we could also collaborate? So challenges that you might have, according to my experience, more than 20 years, as Aviatar was saying, pointing out, making me feeling a bit old in optics and photonics. You may have, let's say, issues or challenges, let's call it challenges, when you have to micro-manufacture miniaturized optical components or systems or devices in 3D. You might have challenges when you want to go from 2.5D free-form micro-optical components to fully 3D miniaturized optical components and systems.
Well, I have just a quick question from my side. Can you maybe emphasize what's the difference between the 2.5D to 3D?
Immediately, well, this will become clear later on, but when you think about micro-optics, as micro-optics is done today, for example, we have some super good examples here in Switzerland with one company which is neighbor of us in Neuchâtel, Swiss Micro-Optics. They do by imprint. So you come with a master, you imprint, and you have your micro-optical, let's say, for example, a micro-lens array on your substrate. This is 2.5D because you don't have the fully third dimension. What we can do at Pemtoprintt, as you will see, we can shape in the fully 3 dimensions. So we have no limitations in the dimensions that we can address. Hope it's clear. It will become more clear with concrete examples later on.
Thanks.
If I continue with challenges, one big challenge, especially for small companies, and this I saw clearly when I found it fabulous, is to find possibilities for feasibility and fast prototyping. Very often when you go to companies that are dealing with volumes, they are not really keen in doing few samples or few prototypes. And that's one point where you might have challenges. And then the next point is when you are stuck in prototyping and want to go to the first series, so what we call pilot manufacturing, up to volume production. Challenges are when you have to look for origination, mastering, and tooling, especially if you're looking for something which is not super expensive. This is as a tooling facility to enable UV imprint, hot embossing, or injection molding. And then the last challenge, if you want, as I was saying before, monolithically integrated many functionalities in your device, so the price per function is decreasing. What are the challenges quickly for Pemtoprintt? Today, we're building up our capabilities in design metrology and functional testing. That's one of the missions of the new divisions in Neuchâtel, which is fully dedicated to optics and photonics. Then challenge for us is every day, responding to requests from customers for fast prototyping, manufacturing, mastering. And then the challenge is whenever customers or partners come with requests for collaboration on development and manufacturing of micro or miniaturized optical components, application-specific photonic systems, and multifunctional glass microsystems. And you see here that our challenges nicely match the challenges that all the potential customers or partners that are online may have. Now, a few words about Pemtoprintt very quickly for those who do not know Pemtoprintt. Pemtoprintt is a contract manufacturer specialized in laser-based micromachining of glass microcomponents. We were founded in 2013 as a startup as a result of a European project. At that time, we were a startup. And one disclaimer, at that time, we started the business model selling machines, but this changed pretty quickly. A couple of years after, there was a radical change. And instead of selling machines, we sell now fabrication services. We do produce machines, but these machines are produced for our production facility. And that's a guarantee for customers. When they want to go to volumes, we can set up production lines that are dedicated, and we can wrap up in production volumes, also building our own systems. And what we are also doing, we are constantly improving our machines and our processes. That's a full, let's say, a full technological roadmap going from process to machine to components. So today we are not anymore a startup, we're a scale-up company. It's what it's called today a scale-up company. We are actually, this is not exact, we are almost 40 people. At the beginning of the year, we'll be 40 people. We have really an organic growth, which was very fast in the last couple of years, to the point that now we have 2 locations, as we were saying, in Switzerland. We have our headquarters in Muzzano, in the south part of Switzerland, where people speak Italian. It's where the company was founded and where the production facility is located. And since this year, we have this division in Neuchâtel, that is dedicated to optics and photonics. We are selling worldwide, and importantly, we are certified ISO 13485, which is the ISO for medical, because the backbone of our business is indeed medtech and life science with a lot of microfluidics. And the second biggest market is watchmaking, since we are a Swiss company. Now we are really ramping up with optics and photonics, and we have really nice plans for optics and photonics in the company in the next few years. Quick introduction in our offer. So I will go through the details in the next slides, but in a nutshell, what we do offer through our micromanufacturing platform are services for 3D microfabrication. We can write things inside the bulk of the glass, typically waveguides, for example. We can drill and cut, we can weld, we can microstructure surfaces, we can ablate metallic thin films. Our competencies goes from the engineering. We have a very strong engineering team. Design for manufacturing is a platform that are currently building up and is intended to actually decrease the number of optimization loops that are required to match the target specifications required by our customers, starting to put the manufacturing intelligence already in the design phase. And this is something very powerful that will help us really decreasing time, be much more effective, and also cheaper for the customers in the early phases, especially in the feasibility phase. Rapid prototyping, manufacturing, obviously we can characterize what we produce, quality control, and then also functional testing.
Orlando, by rapid prototyping, what do you mean roughly?
So our turnaround times are typically when we get a first design, if it's not super complicated, we go from 4 to 8 weeks, depending on the complication and how much engineering we need from the day we start the project to the day when we deliver prototypes to the customer. Typically, we need 3, let's say, I would say 3 to 4 weeks for what we call the non-repeated engineering phase. So we have to adapt our, let's say, we have to optimize the production processes for the specific design of the customer. And then we need a couple of weeks to produce the prototypes. The non-repeated engineering is done only once if the design remains the same. So if the customer wants to have more samples, more prototypes, then the turnaround time is a couple of weeks max. It always depends on the backlog and also on the material. If the glass is very specific, the substrate is very specific, and it requires really sourcing of this to a specific provider, it might take a few weeks for the material sourcing. But these are the timing. The lead times typically a few weeks.
Sure.
So we also tend to vertically integrate technologies that are functional to provide the full solution to the customer. So coatings, dicing, polishing, metrology, packaging, and replication through external partners. Now, we have discussed about what Femtoprint can do, but what is Femtoprint? What is what we call the Femtoprint laser-based micromachining? It's, first of all, something that works in glass. So we exclusively work with glass. It can be fused silica, which is our workhorse, but can be also, as you will see, other types of glass like borosilicas, boroaluminosilicates, and other specific glasses. Here, I summarize the properties of glass that for me are important, specifically for optics and photonics, since today we talked about micro-optics. Glass is transparent, is stable electrically, it's biocompatible, which is important for some biophotonics applications. Here's something for me very important, very nice thermal properties. If I compare, for example, with components done in plastics, glass is not sensitive to any thermal, let's say, any heat dissipation that you might have in your optoelectronic device. It's highly elastic. You see here 2 videos where you see glass flexures that we fabricated with our technology. And actually, with our technology, we can make glass even more flexible than what it is. And if you couple this with some optical elements, it can open up interesting possibilities. I will show a couple of examples at the end of the webinar. It's resistant to corrosion, neutral to magnetic fields. So what is the basic process? So usually we get from the customer a technical drawing, or what we prefer to have is also a step file, so a CAD file. Out of this, we generate the path for the laser to go into write actually the structures to be fabricated into the glass. And how we do this? We do this with a femtosecond laser. It's an infrared laser. Normally, if you shine femtosecond laser through glass, nothing happens. But if you focus the laser very strongly, you create what we call a voxel. A voxel is an ellipsoid, which is typically 3-4 microns large and up to 10 microns high. And you have all the power, the entire power, concentrated in this tiny voxel, which is our pencil. What happens in the voxel is that this high power generates or triggers 2 photon absorption processes. And the 2 photon absorption processes can have several consequences depending on the laser parameters. 2 typical consequences are either the fragilization of the glass or the densification, or both. If the glass is fragilized, that's exactly what we use to write into glass. That's why at the beginning of our story, we called ourselves a 3D printing company. It's more a 3D writing. With the voxel, we write into the glass and we fragilize the glass locally. Once the glass is fragilized, it means it is much more sensitive to what? To etching. So we go into what we call material processing. It's an etching bath, and we remove the glass that is being fragilized. So for example, here you see we create a cavity, but we can also create 3D shapes. We can open channels, and that's how we print into glass. It's a two-step process that can be applied, especially for fused silica. We are really specialized in fused silica, but we work also with borosilicate, for example, BoroFlow 33, which is very much demanded at the moment from people working in silicon photonics. Other glasses like boroaluminosilicates like Eagle XG is a glass that's being used a lot for writing waveguides. I will come to this later on.
Orlando,
what are the advantages?
Yeah, sorry to interrupt you. Just a quick question. So how can you explain about how you get to optical performance?
I will come to this later, but this is through a post-process. So out of this process, you have still a residual roughness, which is in the order of hundreds nanometers, which is not enough for optical applications. What we have developed is a special surface treatment that allows us to reduce the roughness down to 10 microns or below, down to 10 nanometers or below 10 nanometers. So today we can produce components with optical grade. I will give you some examples later on. So the advantages of our technology with respect, for example, in comparison to laser ablation is that with laser ablation, you generate a lot of defects at the surface that with our technology are removed in the second step process. Also, we have a better control on the verticality of the sidewalls, better than 0.1 degrees. We can work the glass in fully 3 dimensions. For example, this compared to other standard technologies like lithography. We can integrate functions. We don't need a clean room. We are maskless. And again, with a third step, we can get excellent surface quality. So here you see an example of how our process works. You have a glass slabs, and then we start writing with, imagine that the pointer is our voxel. So what we do, we write into the glass, and what you see as a dark gray zones are the zones where we have written in the glass, we have fragilized the glass, and then we go into the etching process. And what we do, we singularize the component, and we open up the channels, is the big channel, and here in the middle you have a microfluidic channel. That's how it works. Simple to say, it requires really a lot of know-how. So we have now today more than 10 years, so let's 10 years of experience on the process. And this allows us to do all the things I've told you before. We can 3D manufacture glass with free-form capability and monolithically integrated several functions in one single device. We can write things into the bulk of the glass. That's important for photonics. Come back to this later on. We can weld glass to glass, but also glass to silicon carbide. It's important and interesting for packaging and assembly. We can drill holes and dies. We can generate microstructure surfaces, and we can ablate metals. And here, what you were asking me before. So here are the performances of our technology. In terms of resolution, it's 1 micron. So we are really microstructuring technology. Please don't come to us and ask us to do nanometer-sized things. It's not in our capabilities. We'll let other people with other technologies to do nano-optics. We have tolerances in the order of 1 micron in the plane and 2 microns in the vertical. And this is because we write with a voxel, so it's an ellipsoid. It's higher than larger. That's why we have two types of tolerances. Surface quality already said. Standard process, hundreds nanometers in terms of surface roughness, average surface roughness, post-treatment below 10 nanometers. If you think about drilling holes, we have a hole aspect ratio which goes up to 1 to 500. We can really drill holes through very thick slabs up to 3 centimeters. The minimum hole diameter is 5 microns. Sidewall deviation, as I said, 0.1 degrees, and the sidewall roughness is nice. Is below 100 nanometers, which is better what you can get with laser ablation. And I think that here we said, Aviator, we can have some, just before going to questions, one thing very, very important. We work usually in feasibility phase and prototyping chip by chips or component to component, but our technology, our machines work actually routinely at wafer scale. So we work routinely at 8 inches. We have some examples of things we made at 12 inches. So the machines are already fabricated to work at 12 inches, but at 12 inches, we don't have the same precision we have at 8 inches. So we can run wafer scale volume production, volumes to be discussed, but volume production on 8-inch wafers routinely on our machines. And I think then I stop for the first round of questions, Aviator.
Sure. So, so far there were 2 questions which you already answered them during the slides. Arya was asking if you work with fused silica and UV grade, and the answer is yes. And Eli Maimon was asking about the surface quality. If you can go again to the last slide, you just mentioned it. So prior to the post-process, you get to surface roughness of 100 nanometers, and after post-process that you do, you get to surface roughness of below 10 nanometers.
Right. I will show a few examples.
We have another question from Amnon. Thank you, Amnon.
Aviator, before running to the next question, about the first 2 questions, maybe some comments from my side. First of all, about the material. Fused silica, yes, we work with a lot of different types of fused silica. And as a disclaimer, we are constantly broadening the palette of glasses that can be worked with our process. When we change the optical grade of the glass or which glass, we need to adapt our processes. But when we see traction from a sector or from certain number of customers, we tend to develop our processes and bring the processes the same point of precision and resolution we have in fused silica, also with other types of glasses. It's something we are doing at the moment, for example, which is relevant for photonics, with BorrowFlow 33. Because as I said, this is really requested by people working in silicon photonics. And now we are going to the same type of resolution we have in fused silica with BorrowFlow. About surface quality, it always depends, and you will see later on examples on, let's say, where is requested this surface quality, flat surface or corrugated surface. And when we go to corrugated or 3D surfaces, what are the feature sizes and the shape, the symmetry, and the size? Because when we do the post-treatment, we also modify a bit the shape, and we can introduce also what we call waviness. Just to be clear, let's say if we analyze the spatial frequency of a corrugation of a surface, everything which is below 15 microns, we call it roughness, and everything which is above 15 microns, we call it waviness. So it always requires discussion with the customer and understanding from our side on what is the real quality required and where. But in general, you will see examples. So these 10 nanometers is really what we can get today, even better.
Thank you. I'll go to the next question. So Amnon is asking, what is the maximum and minimum typical component size?
Let's say we do things that are in the order of hundreds, up to several hundreds of microns, up to millimeter, and above, and few millimeters up to centimeters. This thing here, for example, it's a micromechanical component, nothing to do with optics. It's a microfluidic channel, micromechanical actuated, that was used for surgery, and this is 7 centimeters long. So we have the capability to do, for example, a microfluidic channel which is 7 centimeters long. So it always depends.
Okay, and last question for now. There was someone asking if we need structured glass. Can you procure materials, or we need to supply them to you?
So difficult to answer without knowing what you mean with structured glass and how it should be structured. But in general, we can do both. If it requires a specific structuring, we can procure the material, or we can structure ourselves. always to keep in mind, and since we go into material processing step, so etching step, if, for example, you start with some glass component which is microstructured or structured in a certain way, the structure might be affected by the etching. What we are doing today, we are developing processes to protect any type of pre-structuring on the glass during the etching process. This allows us actually to add with our technology features that cannot be added by other technologies and complete the component. In certain cases, other technologies are better suited than our technology for a given component or a given element. But our technology can complete this with additional features, like, for example, as you will see later on, for rules for fibers.
Okay. We have a few more questions, but I think that we will keep them for the end of the webinar. So let's continue with the interesting examples that you have in the next slides.
So, as I said, we start with what they call optic components, going to micro-optics and to wafer tooling. So the first example is what I call miniaturized optics, so millimeter scale optical components. Few people call this, let's say, micro-optics. I'm a bit a Taliban on this. For me, micro-optics is below 1 millimeter. Everything above 1 millimeter is miniaturized optics. And this is actually a realm or a zone, is a gray zone between the typical micro-optics and the standard macro-optics, which is sometimes very challenging. So standard technologies like those used for micro-optics to work out, for example, macro lenses, or processes that are well suited for micro-optics, so several hundreds of microns up to 1 millimeter, struggle to make components like this one. You see the size of these components compared to a euro coin, actually a 2-cent coin. It was few millimeters, couple of millimeters times 3 millimeters. And this is something that is very difficult to achieve with optical quality with injection molding or with imprint. So we developed this glass component in a project with CLED. You will see a lot of things coming from collaborations with institutes. The reason is that I can show only what is done through public projects or projects with public research institutes. It does not mean that we only work with research institutes. Actually, we have many more industrial customers, but I cannot show, unfortunately, what we do for them. So this was an interesting application. They wanted to have a CMOS, let's say, reader to measure pollutants in air, so particles in air. How to do it? They are fabricating a CMOS chip with a hole inside. Through the hole, you have airflow with particles. Then they come with a laser that is deviated, you see here, with a 45 degrees mirror. And when the laser impinges on a particle, the light is scattered. And the light is scattered and collected by the CMOS reader. They needed to have this optical component to improve the signal-to-noise ratio. And the component consisted of two elements. 3 freeform mirrors, you see the 3 freeform mirrors outside, and 3 vertical diopters. The diopters were those that are collecting the light that is scattered by the particle, and the mirrors are focusing the light on the CMOS chip. Already you see here few elements that I told you before. The monolithic integration of 2 types of functions, reflective and refractive, the possibility of fabricating freeform in 3D, and actually the possibility of having the optical component co-packaged or integrated in the packaging, in an optoelectronic packaging on your device. In terms of what we realized, you see the component here, you see here a picture of the diopter and a picture of the mirror. And on the mirror, on the surface of the mirror, we could get an average roughness of 6 nanometers. So pure, perfect optical grade surface. This component was mounted on the CMOS chip, was tested, and it allowed actually, and it did what was meant to do. So improving the signal to noise ratio of the entire device. I do not enter into the details of the device. The important thing is this possibility of doing these miniaturized optical components, and then you go one step forward. The step forward is micro-optics, the main topic of today. So we can do micro lenses, we can do micro lens arrays. You see here a standard micro lens array. Then we can go to more complicated shapes. Here you see, for example, arrays of microcones, or actually truncated microcones. And then we can go to something even more complicated, totally free-form microlens arrays. This is an example of a project we had with CSEM when actually still was at CSEM. Now, the question is immediately, how do we position on the value chain of micro-optics? The first disclaimer is we are not in competition with companies doing micro-optics at high volumes with, for example, imprint or standard reflow and etching technology. I mean, companies like SUS Micro-Optics, Axetris, former AMS, so former Heptagon, today AMS. All this, we are not in competition because we are totally complementary. How? We can offer two things. The first one is feasibility and fast prototyping. What I saw, especially with SMEs when I was founding Fabulous, is that all these companies are struggling because they would like to integrate new micro-optical components in their devices to improve the performances of their devices. And then they go to companies doing micro-optics in volumes. And as I was saying at the beginning, they're struggling to have few prototypes, either because these companies are pretty much booked out for volume production, or because there is another bottleneck, is the cost of the tool. For example, if you want to have imprinted microlenses or injection molded microlenses, you need to have a master. The master can cost up to several tens of thousands of euros, can be very expensive. There's an upfront cost that is too risky when you are in the feasibility of fast prototyping phase. So what we can offer is to do prototypes at low cost, short lead times, in the feasibility and fast prototyping phase. We do not need to have a master. That's the first big advantage we have. And then the other advantage is that once the first prototypes are positive, the customer usually would like to go to some small series to start, for example, qualifying the component with its own customer or running certain tests. And then we can offer this pilot manufacturing. Then the customer wants to go to first series production, we can do this. And if the business is taking off, they usually would like to go to super high volumes. And there we can produce the master for the imprinters. The advantage is that we have absorbed all these risks because the master will be done from not even a prototype, but a first validated product. And then they continue to do the production with the imprinters. That's how we are positioned. In terms of performances, here is what I call the rule of thumb of Fentoprint. In terms of optical quality, if you are on flat surfaces, as I said, we can reach easily average surface roughness below 10 nanometers. If you start corrugating the surface, if, for example, we have a microlens array, then we have to find a compromise between how much we can decrease the roughness and how much we can modify the shape with the post-process. Here is the trade-off. Usually we have an average roughness between 10 and 20 nanometers and a shape accuracy which is between 1 and 3 microns. If we go to fully free-form microlens arrays with high sags, then we have the trade-off with average roughness in the order of 20 nanometers and shape accuracy 2-3 nanometers. That's the rule of thumb.
Rolando, if you go to something else which is not specifically microlens array, like a totally free-form micro optical part,
it's these numbers apply because it's always the trade-off. What is your shape? What is the symmetry? What is the functionality of your device? That's why we are developing this design for manufacturing platform where all these elements will be contained. And when we receive a design from a customer, we'll be able to say, okay, this shape can be fabricated or it cannot, but can be modified in this way with this impact on the optical performance. That's where we want to go. And also all these numbers are currently being improved. So, for example, surface quality is on our technological roadmap in the engineering group, and they are working very hard to improve all these numbers. Today, we are in qualification to be master suppliers with at least 3 big imprinters in Europe. So, concrete examples. This is a small, what I call a small microlens array, so 100 lenslets, diameter 500 microns, sag 50 microns. You see here, after the first process is super rough. Then we apply the post-process and we can get nicely the sag. We can get a very nice surface quality, average roughness, 5 nanometers. The price to pay is the shape accuracy. The same if we go to a larger sample. So here we have 700 lenslets. The ratio between diameter and sag is always the same, 2:1. And then again, the sag can be hit very nicely. Average surface roughness, 7 nanometers, shape accuracy, 1 to 2 microns. So today, what I can say is that we are very much comfortable with microlens arrays with this ratio between diameter and sag, which means shallow microlenses in, let's say, in the field, these are shallow microlens arrays. We can go to higher sags, but there we lose a little bit in shape accuracy. These microlens arrays we see, they are nicely fitted for example, lighting applications or beam shading applications. We are not yet there for imaging applications. This should come, I would say, next year or early 2024. But we have already done, for example, high sags microlens arrays. This is the same sample I've showed you before, totally fully freeform. The lenslet had diameters of 50, 70 microns, is an order of magnitude less than what I showed you before. You see also an order of magnitude higher in terms of numbers of lenslets, and the sag is up to 70 microns. You see that the ratio is not anymore 2:1. Here you see the result after the first part of the process. Average surface roughness 250 nanometers, can be improved down to 20 nanometers or better, losing a bit in shape accuracy. This was not really a problem for this application. Actually, this was used for lighting application, for beam shaping for lighting, and was enough. So it depends also a lot on the type of application you're looking for. So that's the status for miniaturized and micro optics. Now we can go to what I call photonic components, because nowadays when you have a microlens arrays or a miniaturized optical element, it's not anymore enough. You would like to integrate this component into a system, and you need to add up other elements. For example, you need to add up what can be, for example, waveguides. So, and with our technology, we can write waveguides in glass. How? Again, the first part is the same, but when I told you we can focus the laser into the bulk, and we can use different processes through triggering two-photon absorption, one of the processes can be glass densification. So what we can do locally, we can densify the glass, which means we can increase the refractive index. The delta N is typically in the order of 10 to the minus 2, 10 to the minus 3. So you see here, for example, is a locally high, is a spot where locally the refractive index has been increased. If you think about writing this on a stripe, for example, what you're doing, you're writing a waveguide in the bulk of the glass. And it's what we really do. Here you see a waveguide which is written into a glass slabs. You see here a fiber arriving and injecting the light into the waveguide. So today we can do waveguides in glass. I call it photonic wire bonding. Why? Here I'm inspiring to another nice technology, very super nice technology has been developed recently by Vanguard and Ficon-Tech. They can write this, what they call photonic wire bonding, through two-photon absorption in UV sensitive materials. And they use this to connect fiber to chips or chip to chip. Super nice technology. With our technology, we can do something similar with a couple of advantages. First of all, we can write the waveguides in one step, while when you do it with the other technologies, it requires 3 to 5 steps. And our waveguides are already integrated in glass. We don't need to encapsulate them, and are made in glass, which is thermally stable. It's an advantage if you're thinking about, for example, integrated photonics and PICs. And you can also integrate the waveguides that you will see with other elements very easily. Micromechanical alignment components for fibers or micro-optical components. So coming back to the waveguide, some numbers. So we can do single and multi-mode waveguides. At the moment, we are doing this a lot. Actually, our customers are all in the telecom, so 3010 and 5050 nanometers. If you are talking about single mode waveguides, we can have mode field diameters below 10 micron, depending on the wavelength range. Losses, we are in the order of 0.7 dB per centimeter. By end of the year, we try to be at 0.5. We are going to actually present this work on waveguides at Photonics West. And we can, and this is actually something very important, we can make bands or circuits in 3 dimensions. We can really write waveguides in 3 dimensions into glass. In terms of bands, we are limited today for the moment at 25 millimeters in terms of bending radius. This is set because at 25 millimeters, we set the limit to 1 dB per band losses. One comment, all these numbers are for fused silica. They are being improved and also can be improved going to other materials. There are other groups that have already shown, for example, that if you go to borofloat, since you can have a better delta N, you can improve very much losses and also bending radiuses. This is exactly what we are doing now. We are going also in this respect to borofloat.
Orlando, what is the maximum length of
So it depends on your application, but these are waveguides that are meant to do a few millimeters. It's not for long distances. This is these are waveguides that are functional to integrate waveguides, for example, into a photonic integrated circuit or in anything that needs to be coupled or use of photonic integrated circuits to bring light in and out.
Okay.
And as I said, the other advantage of our technology, we can actually combine these waveguides with other elements. We can combine them with a relative positioning error of ±1 micron. And this is because we can do this working on one single machine. So we can write the waveguides and all the components that will be showing in the next 2 slides on the same machine. So we don't have registration problems. So we don't have to make the waveguide on one machine and then go in another machine. So needing, for example, M marks and all these things. That's the big advantage. And we can combine waveguides with what? For example, with micromechanical elements for fiber alignment. Here you see an example. This is a V-groove array for accommodating fibers. And then each V-groove is continuing on the other side. You cannot see because of the contrast in the picture, but here each V-groove is continuing with a waveguide. And again, it's continuing with, let's say, the alignment precision is in the order of 1 micron. You can go one step forward, and then you can also add on the edge microlenses. Here you see microlenses added on the edge of the glass slabs, and each microlens behind is continuing with a waveguide inside the glass. Again, you cannot see the waveguide, which is here, for example, because of the contrast. But you see here, you have a laser light through a fiber is shined into the sample. Every time it's hitting a waveguide and the micro-optics, you see a nice spot appearing here. So at the end, what you can have is a full integrated system when you can have your waveguide, you can have a V-groove or a ferrule to accommodate your fiber, and then you can have a beam shaping element to bring the light in or out of your photonic device. With, again, 1 micron precision in monolithic integration of all these elements.
I'll just discuss it for a second.
Yep.
Everyone can continue ask questions during the slides. We'll get to them in the end of the webinar. And Orlando, we are a little bit tight on time, so let's try to be a bit quicker.
Okay, I will speed up. So there are 2 chapters remaining. One is I already introduced fiber components. So as I said, we can do V-grooves, but we can also go a step farther. We can do ferrules or 2D hole arrays for 2D fiber arrays. You see here, these are things that we do routinely. These are standard products for us, and we have a lot of requests at the moment, and I will explain you why. But here, the advantage we have with respect to other technologies, we can produce 2D fiber arrays, which are fully customized. So you can have, for example, holes at different angles. We can do this through very thick slabs, which is an advantage in assembly and packaging. And we can have a micron precision in diameter and hole positioning. We'll come back to this in the next slides, but before going there, just this example, I find it nice. This was a request from MIT. They wanted to have a fiber array system for an imaging, to create actually an imaging system for a spectrograph for an astronomical telescope. Here, what we did for first a V groove with 2084 grooves to accommodate the fibers. The fibers were going down and going to a second plate that we made. It's a 2D hole array with 2084 holes to accommodate the fibers. Imagine the PhD who had to put all the fibers in. And the nicest thing is that this is coupled with a third element, another slab, another plate that is containing a micro-optical element. And these two plates were combined through pins with micron precision. And in the end, you have a fully integrated fiber array with coupled with a microlens array, giving you an imaging system. So I was saying that we are required more and more by customers to have submicron precision in hole position and hole diameter. And why? Because in integrated photonics, the trend is to miniaturize everything. On one hand, you want to have more fibers going into the same chip. So you're going to use single mode fibers. You can put them closer. And then you want to have smaller chips. And this because you want to have faster chips, and also you want to reduce the energy consumption, which means that at the end you end up with having a single mode fiber with a mode with few microns in terms of diameter in front of a chip with pixel of few microns. If you have already 1 micron misalignment, you are off specs with respect to the standards for telecom in terms of losses. That's why customers want to have this type of precision that they cannot find with other technologies. And talking here not about V grooves, but 2D fiber arrays. So today what we can offer are 2D fiber arrays where on, for example, hole diameter. You see here examples with hole diameters which are matching the diameter of single mode fibers with submicron control. So we have a control on the diameter, on the circularity, and on the diameter, which is in the order of 1 micron or better. We can also control very nicely the shape of the hole inside the hole in order to avoid, for example, this hourglass effect that would be detrimental because the fiber can enter, but it will stop in the middle. So we have a control on the cylindricity of the holes inside the entire hole, which is better than 0.5 degrees. And again, we have checked also the repeatability of the control on diameter on an array of 11, for example, times 16 holes. We have a very nice narrow distribution of the diameter around the target value, and the circularity is better than what can be measured with an optical microscope. The resolution is in the order of microns, so we are better than 1 micron. We repeat it also on several arrays, and we have, let's say, the average diameter is on target, the standard deviation is better than 0.2 microns, and the circularity, again, is better on the resolution of the microscope. So submicron control on hole diameter, but also nice control on hole positioning, which is the second parameter. Again, we made an array with several holes, and we have an hole positioning hole to hole that is better of the resolution of the microscope we use, which is in the order of 1 micron. So we can claim we are submicron in control of the hole positioning. And repeating this on several arrays, we can have an average hole positioning, which is better than 1 micron, standard deviation better than 0.5 microns. And again, the relative error is at the limit of the resolution of the microscope. Having said that, the other thing we are doing now, we are developing this also to couple with waveguides. All the fiber arrays that I've shown you so far with the highest precision are done in fused silica. We are now also moving in this case to bore float, but mainly they're done right in the holes vertically. If you want to couple the ferrules with waveguides, you need to write the holes horizontally. So with the voxel moving horizontally in the glass. So it's what we are developing now to reach the same precision we have with the standard ferrules. And at the end, we'll have very precise ferrules where you can insert your fiber, and at the end, you can continue, for example, with a waveguide. And also what we are doing, we are developing also tapering and mode field accommodation from the ferrule to the waveguide. Now, just very quickly, ending with the concept of integrating several functionalities. I said you at the beginning, it's one of the unique selling point of the best take-home message for femtoprint technology. 3 examples. Here I show an example where we were integrating microfluidic functionality with optical functionalities. Again, was a project with CA. That's a microfluidic channel And here you see on the sides, fiber inlets and micro lenses. The idea was to put a fiber, shine light through the microfluidic channel, collecting the light on the other side, sending to a spectrometer and analyzing. You do let's say several sections with different lengths. You apply Lambert-Beer law. You can measure the absorptions. You can go to and know what is circulating actually in the microfluidic channel. And here, this was done on 2 different slabs that then were combined and welded together with micron precision. So here you have really 3 functionalities at the price of 1 component. It's microfluidic, micro-optical, and micromechanical plus welding. You can also integrate with micromechanical functionalities. 2 examples. Here you see a glass component which has a central part, a circular central part that is connected to an outer ring by 3 glass flexures. So this part can vibrate. This part was actually coated with a metal and it was a mirror. And this was used to measure gravitational waves. Another example is an optical accelerometer. You have an inlet for a fiber. You have a mast which is connected to the rest of the device through two flexures. So this can vibrate and you can read the signal optically. Again, 2 functionalities, micromechanical and micro-optics. And the final one is integrating with electrical functionalities. I finished with this because this is very a la mode. It's trendy. These cavities here are nothing else than ion traps for quantum. Today we have a lot of customers worldwide, starting from research institutes in Europe, very known, to companies that ask us to produce ion traps. For 2 reasons. First one is that with our technology, we can produce perfect cavities. You need to have perfect cavities not to disturb the ions. And we have developed the laser ablation technology to actually create 3-dimensional metallic contacts into the cavities to address the ions. So again, 2 functionalities, optical, actually 3 optical, micromechanical, and electrical combined in the same component. And I think with this, I'm done, Aviator.
Thank you very much, Orlando. Just before we go to the questions, which we have now a few, I'll hear the details if you would like to contact us personally or privately. You can go to the last slide. So here we leave this as a slide for asking more questions, and I'll go right away to the questions which are asked so far. So Orlando, I'm going to shoot some questions toward you.
Shoot.
I hope you're ready.
I'm ready.
Have you supplied the service to consumer applications?
Yes, we have 1 customer at the moment in the consumer application world. It always depends also on the volumes required, but at least in feasibility and prototyping, we work with customers that are targeting super high volumes in consumer electronics or, for example, in telecom.
I guess this is more smaller parts in size, right?
Yes.
Thank you. Yuval is asking, what is the throughput for such a manufacturing? Let's say on a wafer scale. Alternatively, what is the aerial speed? So,
in terms of speed, these are not really information we usually disclose, but I mean, to write components depends always on the symmetry, on the complication. It can go from a couple of minutes to some hours. Throughput, it also depends on the product, but what I can say today that our technology is done to work with quantities that can be several thousands, several tens of thousands, up to several hundreds of thousands per year per product. We are not, I think, at least for the moment, made for the millions of components per year, which is the typical throughput, for example, for technologies like imprint, if I'm talking about micro-optics.
Mm-hmm. Okay. Ophir is asking, what about coatings? What types of coatings can be applied on these components? Do you also coat the parts? And could a shape with different elements on it, different lenses or mirrors, be coated with different coating types on each element?
So as I said, we are integrating vertically some technology with coatings, but with some disclaimers. We have some capabilities because we have access to some facilities where we can do some coatings, but these are very simple, for example, anti-reflective coatings. When it goes to very specific coatings, especially for optics and photonics, we usually rely on external suppliers. And so it depends on the glass, it depends on also the roughness. I mean, if you need to coat, for example, with a metallic coating or multi-layer coating, you need to start with a very smooth surface. So we need to really have optical grade, and then the coating can be applied as on any other type of glass. So this depends on the glass and the shape and the functionality. This can be discussed case by case. I think it's difficult to discuss on a general level.
Yeah, I agree. Arya is asking, is there a limit on element size? Total element size, for instance, 5 by 5 centimeters or 10 by 10 centimeters?
I mean, there's no limit in the sense that we work up to 8 inches in wafers. So you can have a full wafer. The feature size is always a trade-off. How much you have to write per size, because at the end, the cost of the component depends merely on the writing time.
Mm-hmm. Amnon is asking, could you show an example of a component designed by optical simulation versus a real product outcome? Our product is adequate versus simulation.
Yes and no. Yes, I could show, but I cannot, because otherwise I would be killed by a couple of lawyers and I would lose my job. So that's not possible.
Do you have something which is published by a university or anything like that?
I should check. If there is a specific question on this, you contact me, and then we
can come back to you privately.
Exactly.
As an example. Nitan is asking, excellent surface quality. What would be the wavefront for a planar surface?
Oh, that's a super good question, a super difficult one.
Nitan is asking questions always.
Yeah, because I mean, I'm afraid I cannot answer. I cannot give you numbers, because also it depends on the application of the component. We have a couple of customers, they are measuring the wavefront error distortion for their application. But as said, when you want to be lambda 20, 30, 40, it depends on the surface you need. We might be at the limit of our technology for the moment, because we can smooth, as I said, but we will always also introduce waviness. But again, this must be discussed case by case. It's very difficult to give you a general answer on this.
Okay, so I think that we can discuss this separately.
Absolutely.
Another question from Arya. How long is the manufacturing time? I think that this was a bit...
as I said, it can be minutes, up to a few hours. It depends. By the way, our machines run 24/7. So.
Okay. So this is all of the questions. Sarit, thank you for joining us. Any other questions before we finish? If not, so thank you to everyone who joined us today. And especially thank you, Rolando, for joining us.
It was a pleasure to be here with you guys.
Yeah, and as you can see, the Israeli market and players is growing and has a very good appearance even worldwide. So yeah, I'm happy for that.
And looking forward to meet you in person in San Francisco, Photonics West. Finally, we go back to normal.
If any of you guys that are attending will be in Photonics West, we'll be happy to meet you there. And one last thing, next week we have Oasis exhibition. You are welcome to come to our booth and see some examples and of the Pemtoprintt results. We have some micro lens arrays and other components such as the ones that you've seen here in the presentation, here in the webinar today. So you're welcome to be there and meet us in person and see some actual parts. Okay.
Thank you very much.
Thank you, Anton. Have a
Have
great
a nice day to everybody. Bye-bye.
Bye-bye.